So Google search, which was cloudy days per year, Bureau of Meteorology, we ended up with this for Melbourne. And probably that's good enough for every area within that circle. And sunny days, we've got to get this proportion. So I'll have to interpret those figures and punch them into my calculator, because spreadsheet can do it. If you're not using spreadsheet in your life, well, you must have a cushy, good for nothing, useless feeder job, is all I can say. So here it is, downloadable too. Had a CSV file. Yes, I've punched in another site. This time it's up here on the Murray River, and there it is again. The mean number of clear days and cloudy days. Doesn't have sunshine. What's going on? All right, let's go and choose another site. So I've gone into rainfall, and unfortunately we're talking millimetres now, so we'll get out of here. I find that the airports generally have the best data. Mildura's nearby, that could do it. And this weather station has the material I need. So I'll have to do several over the course of Victoria, and then every state in Australia if I wanted to go nationwide. And those sunshine hours, let me interpret. How would I interpret those? Is that direct sunlight? What are they talking here? They must be. It must be direct sunlight. So you're averaging about 10.8 sunny hours a day. What do you mean? In June 5, 10.8. Is that cloud? Oh yeah, this is Mildura. Yes, that does make sense. This is semi-arid desert area up here. Those statistics are very close to actually sunrise, sunset. Yes, no, this is what we need. This is what we need, all right. And I'm going to punch it into my spreadsheet, and that's going to be great. Then I only have to answer the next question. Look at that. I found the NOAA solar calculator. Came up in my search for sun irradiation, sunrise to sunset. So I've got to account for that as well. This thing won't load at the moment. It's probably because I'm in Australia and we have crap internet. Anyway. Oh, look at this. Woo! So we're, what are we talking about here? We've got 365 days of the year here. In the middle, we've got, the middle of the year. Now, what latitude are we? We're up north here. We're going to down minus. We're going to go about Melbourne there. So what does this mean? Radiation. Yeah, that's right. This is winter. This is winter here. That's summer in the northern hemisphere. Yeah, that makes sense. I'm going to go here because it makes sense to me. I can cross-reference it pretty easily. So there's summer, and this is our horizontal line. An incident. Look at that. So I've been playing around with this tilt angle. So there you go. So we've got, I guess the red is the incident angle of the solar on a horizontal surface, because that's not really moving. But the module irradiation is. This is the tilt angle, and it only does directly north or south. So fortunately my calculator is safe from some online app that can do everything mine's doing at the moment. We'll continue. The module is assumed to face the equator, so that it faces south in the northern hemisphere and north in the southern hemisphere. As the latitude is adjusted, so this is for one orientation. Yes, okay, directly overhead we have an air mass of 1. Now this is what I'm looking for to throw in. And I've got sunrise to sunset. I've got plenty of orientation data. So all I have to do is apply the factor. Right, so it's just 1 over cos, eh? Air mass equals 1 over cos of the angle. This is a factor. Yeah, well, okay, once I've got that factor, how much percentage of my sunlight is that going to crop? Okay, I've got a calculator here. And the cos of 45 is 0.787, blah, blah, blah. If I go 1 divided by the cos of 45, I get 1.4 blah blah blah. So let's punch in, see if we get 1.41 here at 45 degrees. Yeah, we do. So that's just a very basic calculation. So that's a ratio. It's a proportion. It doesn't tell, but then I've got to add how much this, or should I say a factor, a multiplier. Let's say with every atmosphere of 0.1 or every time I double the thickness of the atmosphere, how much irradiation am I going to lose? Well, I think I'm going to have to go to solar radiation in space. If they're not going to give me that figure, deduct the terrestrial solar radiation from it at directly overhead to get a freaking answer. Somebody's got to have this shit. See, as you can see, I'm asking all the right questions. That's the genius of what I'm doing, just knowing what questions to freaking ask. The rest is just follow through. Spacey stuff we don't have to worry about. What we need to get is this. It's 1.36 kilowatts per square meters at the Earth's atmosphere. So once it's been through the Earth's atmosphere, it's 1,000 watts a square meter, or 1.0 kilowatts per square meter. So there's my ratio. It's basically that. That's the difference. So what that means is I'm losing 360 watts through that length of atmosphere. So that means if, whatever that is, what was our earlier example? 41% more atmosphere. So that means 360 watts multiplied an extra 41%. Here we go. So I'm losing another, 147 watts per square meter from directly overhead. That's significant. That is pretty harsh. I think I'm going to have to double check that one. So here we have the sun rising and sun setting on what is obviously the flat Earth. As we all know, what we haven't figured out yet is why the sun doesn't fall out of the sky. We're working on it, us flat earthers. And the moon, we don't know why that hasn't fallen out of the sky yet. And why the sun, as you can see, as it disappears over this horizon and that horizon, doesn't melt the massive ice wall at each end so the water doesn't fall out, the oceans don't empty. So we haven't worked that out yet, but I think there's 200 scientists working around the clock on it. They'll update you soon. In the meantime, we've got to work out this air mass issue. And you know what that means when it comes back to this sun tracker data? That means the last step in my trigonometry was, of course, inverse sine, because the sine of the incident angle of the sun onto the panel is proportional to the watts per square meter. Get that into an angle again, or get it while it is an angle before I've turned it into a proportion of kilowatts per square meter, and get 1 divided by the cos of that angle to get my air mass issues solved on each and every single one of these. So that's going to end up right back at the source. Then, once I've got that sorted, and I've got relatively accurate kilowatt hours per square meter ratios here, that means I've got to separate perhaps in 2 lines. We saw the Mildura had, for example, in January, an average of 10.6 sunny hours, direct sunlight. That means, I don't know, in summer up there, it's like, good 14 hours, I reckon, of sunlight, let's say. So that means there's going to be 4 hours of cloud averaged per day over that month. And that has to be separated into whatever this adds up to. That'll be relative to our sunny days. And then I've got to work out a proportion of this total peak sun hours per month that sunny day component will take up. Then I have to go over here, back to this page, and crop the inverted generation readings from obviously the sunny days. This one here is going to end up, that line there, inverted generation, is going to have to go over here on this sheet in with this lot. Yeah, I'm doing these videos because, you know, I want very, very accurate figures. The only figure then I can't calculate is the shade on an array. That is very variable because, you know, we've got a row of panels that could be 10 meters long, and the shadow on the first panel is irrelevant to the shadow on the last panel 10 meters away. Completely irrelevant. I don't know if anyone's published it. Someone's done, that's actually going to have to be done by data collection. Now, no one's done it. No one's put 10 panels in a row with a tree in the middle, or a tree at the east end, or a tree at the west end, or a chimney here, a chimney there. No one's actually done a graph that you could plug into this sort of spreadsheet to calculate the effects of shadow. And if I go and do a tracer of the horizon from a set point, which a lot of solar software does do, you go and point your phone at the bloody horizon that's been around for decades and follow it, well, that's at one point. It's not at each end of a 10 meter row panel. So, But before I go, the sun's position to high accuracy. Back on this page again, the education page. It's called pveducation.org. If you want to go look it up. And they've got a bit of a disclaimer too, because obviously I'm compiling a lot of data that it's just sporadic. It's here, there, everywhere. I'm putting it all into one to get meaningful figures. How much is your bill going to be with or without solar? That's what my spreadsheet does. No one's really put it together. They've got factors here, factors there, this, that, the other thing. This one here's, the disclaimer is flat modules, only accurate to a few degrees, doesn't have the Bureau of Meteorology factors put in there, etc., etc. But it has given me a lot of good information. So if you want to learn about it, this is a pretty good site. pveducation.org. See you later.